Hi all, welcome back. So today in this lecture we are going to learn about partition allocation method. Actually it's a very small topic which is related to contiguous memory allocation part. That we talked about in the last lectures about the fixed partitioning scheme and the variable partitioning scheme. So it is a very small topic which is related to how we are doing the partitioning. Okay, so basically for partitioning the memory we are following different approaches. First approach is like first fit. So inside this first fit approach, we find the we start to allocate the process from the beginning, and in the first sufficient space, we allocate that process, the particular part in the first sufficient partition. We allocate the process. Okay, so first sufficient partition from top of the memory. Okay, we'll see how this happens. First, let's discuss about all of these in a brief. So, the first sufficient partition from the top of the memory. Okay, that is called the first fit. So, in first fit, what we see? First sufficient partition from top. First sufficient partition from top of the memory. And in this way, we are allocating the processes, the partition space. Okay, allocating process partition beginning from the first sufficient partition from the top. Okay, so this is about first fit. The second mode of partition allocation method is best fit. So in best fit, what we do, that we find the best sufficient partition by a by a quick scan throughout the partitions, all the partitions that are being made, and find the best fit for the process, and then allocate that partition to the process. So in short, we can write it as allocate the process, allocate the process in a partition which is smallest sufficient. Okay, which is smallest sufficient among all the partition that is being made, which is smallest sufficient among all the free available partitions, among all the free available partitions. So allocate the process a partition which is the smallest sufficient among all the free available partitions, right? So this is called the best fit approach, where we are allocating process a partition which is the smallest sufficient among all the free available partition. What we do in first fit we allocate the process in a partition which is scanning from the top, which is the first sufficient partition. Now we'll learn about what does this sufficient partition means. So we don't see here about the smallest sufficient partition, but in best fit we allocate the process in a partition which is smallest sufficient partition among the all available partition. The third one is one more thing, to find the smallest sufficient partition, to find the smallest sufficient partition, we scan through the entire space, we scan the entire partitions, or you can write it as all the free available partitions, and choose the smallest sufficient partition, smallest sufficient partition among all the free available partitions, among all the free available partitions. Okay. So to find the smallest sufficient partition, we scan the entire partition and choose the smallest sufficient partition among all the free available partition. This is about the best fit partition scheme. The third one is worst fit. So this one was the best fit and this is the worst fit. And in worst fit mode of partitioning scheme, we allocate the process in a partition that is the largest sufficient partition among all the free available partition. So allocate the process in a partition which is the largest sufficient partition, largest means the biggest and sufficient means in which the process can be accommodated. So which is the largest sufficient partition among all the free available partitions, among all the free available partitions. Okay. So in WASFIT, what we do, we allocate the process in a partition which is the largest sufficient partition among the all free available partition. Again, for finding the WASFIT partition, we need to scan the entire all the free partitions in the memory. So to find the largest sufficient partition, to find the largest sufficient partition, need to scan all the free available partitions. Okay, in the memory. Okay, let's add it in the memory. Right. So to find the largest sufficient partition, we need to scan all the free available partitions in the memory. To find the smallest sufficient partitions also, we need to scan the entire partition and choose the smallest sufficient partition among the free available partition in the memory. Right. However, for first fit, we need not to scan. We can just take from the top, we can take the first sufficient partition and we can allocate the process into that partition. Right. Now, the fourth mode of partition allocation method is next fit. So in next fit, we allocate the process into a partition which is next sufficient from the last allocation point. Okay, or you can write it as thinking of it as it works like the first fit, but it will start the search not from the top, but it will start the search from the first sufficient partition from the last allocation point. So the process we allocate the process into a partition which is the first sufficient partition But here, one difference comes that we are not supposed to choose the first sufficient partition from the top, but we are choosing the first sufficient partition from the next allocation point, from the last allocation point, okay? From the last allocation point. Okay, we will see each of them in detail. It was just a summary of all. So it works just like the first fit. However, it will search for first sufficient partition from the last location point. Now, to take a look into each of this, we'll take an example where we have memory. So let's say we have already some partitions being made into this memory. Okay, so let's say this is 8 KB, right? Then we have something, some busy space, I mean, some space being occupied by the process. Then we have this 12 KB. Okay, again, we have this space being occupied by some another process. So this is a busy space. Then we have this 22 KB. And again, we have some space being occupied by another process. Then we have 18 KB. Okay, and then we have some space being occupied by another process. Okay, and then we have this space is the last allocation point. Okay, so this is our last allocation point from where we lastly allocated the process. Any, so we are just choosing this point as the last allocation point. Actually, this is called the last allocation point because at this point only we lastly allocated any process. Then we have this 8 KB space which is left for any process. Then again, this space is being occupied by another process. Okay, currently in running state. Then we have the 6 KB space. Again, we have the space being occupied by another process. So the space is being occupied by another process. After that, we have this 14 KB. And then we have the space being occupied by another process. Meanwhile, running state. And again, we have some space, and in this space we have been left with 36 KB. Okay, so this is one remaining space. So this is our diagram from 8 KB till 36 KB. Okay, now let's see if a process comes, let's say P1 that comes up to us, and whatever, this is the busy part. Okay, so this is busy already being occupied. Let's say we have a process which comes to us after this at this state. So it requires some 16 KB. So based upon the allocation schemes, which partition we need to choose for this process. So let's say if we choose the first fit uh, allocation scheme, so in first fit we will be allocating the 16 KB process to which one? So we will start from the top. So we will see 8 KB, is it sufficient? No. We will see 12 KB, is it sufficient? No. We will see 22 KB, is it sufficient? Yes. So for first fit we will allocate it into this 22 KB space. Okay, because this is the first sufficient space, first sufficient partition from the top. Okay, so for first fit we will go for 22 KB. Next, for best fit, we will find out, we will scan the entire available partition, and we will find choose the smallest sufficient partition for P1. So from this, if you scan down, I think it is 18 KB is the smallest sufficient partition for 16 KB, right? So we will choose this one. So we will, for best fit, we will allocate this 18 KB partition to our process 16 KB. Then we have the WASFIT allocation method, and according to the WASFIT allocation method, we will again scan from the top to bottom, and we'll find the largest sufficient partition for our process. So from top to bottom, the largest sufficient partition is definitely 36 kb. So we will allocate this 36 kb partition to our process P1. Okay. So this will be chosen for was fit, right? Now comes the next fit. And for next fit, I already have told you that it works just like first fit. But in first fit, we scan from top and find the sufficient partition for our process. But in next fit, what we do, we scan from the last allocation point, and then we find the smallest sufficient, not the smallest, but the sufficient partition uh, for our process. So is 8 kb, so this is the last allocation point. So 8 kb, is it sufficient for 16 kb? No. 6 kb? No. 14 kb? No. 36 kb? Yes. So for next fit also, we will allocate our process into this 36 kb space. So this is how best for all these allocation partition allocation method works. And for any process, we allocate it into a particular partition based upon this partition allocation method. Okay. There is one more question based on that. Let's see for that question also meanwhile. So if we start with that, let's see the second question. And it is something like how many successive requests of 6 kb, how many successive requests of 6 kb will be satisfied using first fit variable partitioning scheme. Okay. So for this, for how many successive requests of 6 kb will be satisfied using first fit variable partitioning scheme, we need to go back to this diagram and choose the first fit operation for this. So now our process has 6 kb of requirement, and we are choosing the first fit partitioning scheme. So starting from the top, if we see, for this space we can allocate for one time. Okay. Again this 6 kb request comes up, and the remaining space, if we allocate 6 kb here, is 2 kb, so we can't allocate here. So in 12 kb we can allocate two times. Okay. So this is full, this is full. Then comes to 22 kb. Here we can allocate 6 kb process three times, like 6 times 3 is 18. So for three times we can allocate into this process, into this partition. Okay. So this is also filled. Now it is left with 18, it is left with 4 kb space, so it is of no use to us. So now we can allocate three times into this 18 kb space. So again it will come as three times into 18 kb space. I mean, three times we can allocate 6 kb process into this space. Now comes to 8 kb, and from 8 kb, now you know we are moving down because we already have covered up all the previous space. Okay, so the next available space is this one. So into this we can allocate only one time. Okay, and into this space we can allocate one time. So now these two are filled, and now the available space to us is 14 kb. So inside 14 kb we can allocate two times. So let's add here 2. Okay. And after 14 kb is filled, we can allocate six times into this 36 kb. So let's add 6 again into this. So altogether, how much it is? So 3 plus 3, 6 plus 3, 9, 10, 11, 12, 13, and 13 plus 6, 19. So for this question, our answer will be 19. So since it was a first fit variable partitioning scheme, so we just have to look down from the top. Otherwise, for best fit, we need to choose the smallest sufficient partition, scanning throughout the available partitions. And for WASFIT, it would have been much difficult to choose the largest sufficient partition. And for next fit also, it will be 19 only, because we need to just look at to the last allocation point. So the last allocation point would be always the same as the first fit approach, right? So this way it comes down to 19. Now let's say we have another separate example, like we have this memory map coming like this, and in this we have some processes already running and some free space being left. So let's look into this. So this is 150 kb free space left, and this is 350 kb, that is the space being left, and this is the space which is busy. Okay, so 0 to 1, this is again the space is also occupied. So this is 2 to 3, and this space is also being occupied. Okay, it's 4. Okay, now this is 150 kb and 350 kb is free. So requests from processes are coming in this format, like 300 kb, then we have 25 kb, then we have 125 kb, and then we have 50 kb, and we need to satisfy all these requests. So which approach or which allocation method, partitioning method we need to choose to accommodate all these requests? So let's start with first fit. So if we choose first fit, right, if we choose first fit approach, then what will happen, 300 kb will be allocated into this space. So after allocating 300 kb into this, we will be left with 50 kb, right? Okay, let me draw like a tree structure. So inside 350 kb we will be allocating 300 kb, so the remaining will be leaving as 50 kb, right? So we are left with 50 kb. So in this 50 kb, can we accommodate 25 kb? Yes. So after allocating 25 kb, we will be left with 25 kb. Okay, now, with this 25, can we satisfy 125 kb? No. This 50 kb? No. So, with first fit, it is not possible. Okay, then comes the best fit. So if we start allocating with the best fit, then we will find for 300 kb it is 350 kb, obviously. So 350 kb is the best fit, and then we will be left with how much kb? 50 kb, right? Now with 50 kb, can we satisfy 25 kb? Yes. So 25 kb we will be using up, and then we will be remaining with 25 kb. Now with 25 kb again we will be having the same problem. We can't accommodate 125 kb or 50 kb. So obviously we can't choose best fit. Now let's come back to uh was fit. Okay, so this is the was fit part, and for was fit, obviously we will be choosing the highest largest sufficient space for this. So this is 350 kb. After choosing 350 kb, we will be left with how much? Okay, I'm really sorry. For first fit, we didn't account it for this part, right? Let me account for that. Or let's do a thing. Let me sorry, I didn't account it for this part. So just a second. Let me illustrate it again. Sorry for the confusion. So because I didn't saw this 150 kb, so it was also there, right? Okay, so let's start with first fit. If we go with first fit, then the very first partition is 150 kb. For 300 kb, it is not sufficient, so we will go for 350 kb, right? So let me draw it here so that it is easier to identify. So this is 150 kb and this is 350 kb, right? So we will be allocating 300 kb into this 300 kb, and we will be remaining with 50 kb. For 50 kb, this for 25 kb again comes, and we can allocate it here, like 25 kb we can accommodate here, and 125 kb is remaining. Okay, and here what is remaining? So 300 kb we have already given, so this is 50 kb is remaining, right? Now comes the 125 kb, so here we can accommodate it. Okay, because it is first fit, so we are choosing from the top. So here also it is accumulated. Now comes the 50 kb, and we can accumulate it here, so it is also fitted very well. So all our processes are fitted very well for first fit. Let's see for before was fit, let's see for best fit. Okay, so in best fit, what will happen? We will choose the smallest sufficient space from the top. So this is 150 kb, and this is 350 kb. So this 300 kb comes, and we allocate 300 kb here, and we are left with 50 kb. So this is occupied, and we are left with 50 kb here and 150 kb here. For 25 kb, we will scan from top, and we find that 50 kb is the best sufficient space for allocating 25 kb. So we will allocate this 25 kb here, and we are left with this 25 kb. Now comes the 125 kb, and we will allocate 125 kb here, and this will be allocated, and we are left with 25 kb here. So this is 25 kb left in this space, upper partition, and 25 kb left in down partition. But if 50 kb we want to accumulate here, we can't take combine these two and accumulate this 50 kb process space into this. So this is a case of external fragmentation. Okay, so this is a case of external fragmentation, and hence best fit is not suitable for this set of processes, right? So we can't choose best fit. Let's see for worst fit. So worst fit, here we have the space 150 kb and 350 kb. Now 300 kb comes, and we allocate it into this. So here we are left with 50 kb. 25 kb comes, and we allocate it here. So we are left with 125 kb. Now 125 kb comes, and we are allocating it obviously here. So this 125 kb also gone, and then 50 kb comes, and this is also accumulated. So was fit also behaves good in this scenario. So first fit and worst fit behaves good, but best fit doesn't. So don't go for the name that it is best fit, so it will be always best. For some scenario it doesn't performs the best, right? So in this case we can say that first fit is a suitable allocation scheme for this, and as well as the worst fit, but not best fit. If possible, we can also see for the next fit also. So if we are allocating it into the next fit, so it is 150 kb and it is 350 kb. So first process comes with request 300 kb, so here 300 kb gone and 50 kb is remaining. Okay, because we can't accumulate here. Now we have accumulated the we have done the processing from here. So from here we can see what is the next best fit for that, I mean next fit for that. So obviously we don't have any space for these two from the next allocation point. So if 25 kb comes here, we can accumulate this 25 kb, and remaining is 25 kb. Okay, but this is the last allocation point. Okay, from here we need to find the sufficient space uh, for our process with a request of 125 kb, and here if you see it is already occupied here, so we can't accumulate any process into this. So also we can say that next fit is not suitable for this case of allocation of this processes, right? So on only the suitable candidates for this random set of processes is first fit and worst fit, right? So this is the illustration of different allocation models, different partitioning schemes that we choose for allocating process the space. So that's all for this lecture, and thank you very much for watching. And please do like, share, subscribe, and comment. If you have any doubt or question, keep watching. Thank you.